Okay, so chapter 5, which is about work and energy. So that first video that I sent is really going to say everything that I wanted to say about this relationship between work and force. Really better than I could have said it, and with better animations too. Uh, I do want to point out a little bit more about this relationship. So why is work being brought up? Well, because work is kind of the the connecting piece between force, which we've investigated, and energy. And we'll see that the net force of the net weight, oh my goodness, not weight either, the overall work done by forces is going to equal change in kinetic energy. So we'll see that. So work is going to be kind of that connecting piece between force and energy. So I wanted to say a little bit more about this. Okay, so first of all, the delta x, it should really be a delta x. The slides use x, and the video made more sense to use d for displacement, which is more appropriate than just using x. Because work does not happen at a particular point x, it happens over a displacement, a change in x values, so a delta x. So really, using d is good for displacement, but using x is not good because x means like a point, whereas delta x means an actual displacement. So I'll probably use delta x in this lecture or I'll just use delta in general for the change in energies or the change in position, etc. So I want to talk a little bit more about this cosine theta thing too. This just tells you that the force should be, the work is going to depend on the direction of the force. So if they're going in the same direction, so if some force is applied to some object, then the angle here would be, well, if the force is applied this way to this object and the object's displacement is also to the right, is in same direction, so if the displacement was also that way, if the object was actually moving that way in the same direction as force, then the angle is just 0 degrees and cosine of 0 is 1. So that's like the nice case when work is just equal to force times delta x. Now if I have some force pushing this way, some force pushing this way, but for whatever reason that force is not moving the object, and maybe the object is moving up like this for some reason due to some other force, then this force is doing no work. If objects, so it's, well, let me say this first. If object's displacement is perpendicular to a given force, then work done by that force is 0. By that force is 0. Why? Because here theta is equal to 90 degrees and cosine of 90 is 0. Okay, so it's relative, work is relative to whatever the force is, right? So there is work being done here by a different force that's pointing up. But if I'm just zeroing in on this force that's pushing to the right, but the object is moving perpendicular to this force, then the work done by this force is 0. Okay. A little bit more about the units here, just in case that wasn't clear. Work is measured in Newton meters, Newton times meters, right? Force times displacement, so Newton meters, or joules, just a new measurement, which we denote with a capital J. So more than likely you'll be seeing it written as joules. All right, so let me talk a little bit about this net force idea. So net work idea. The net work for an object should be equal to whatever the net force is times displacement. Now, if there is a net force, right, if not, everything's just zero, which isn't very interesting, right? So if there's a net force, we know by Newton's second law that net force should be equal to ma. So I get that the net work is equal to ma delta x, and then from here is where we derive this kinetic energy relationship with net work. So that's what I'm about to do here. So the first step is to note just this one little step here, that force is equal to ma. So net work overall, is equal to mass times the overall acceleration of the object times the object's displacement. And then I can say, oh yeah, that's I see a delta x, and maybe I recall that I have a kinematic equation that has an a times delta x built into it. So I can say, I can isolate a delta x and just plug it in here for a delta x. And why am I doing that? Well, it gives me this new relationship. Instead of with acceleration and position, I'm getting a new relationship with a difference in velocities. Here, an initial and a final velocity. And if I can get new relationships using velocity instead of acceleration and position, then I'm going to try to do that. So here I'm going to have m times a delta x, but a delta x is equal to this thing. So I have v final squared minus v initial squared all over 2. So I'm getting that if I expand this fraction, that I'll send m to both of these. There's a 1/2 attached to both of the fractions, or rather both of the terms. 1/2, there's an m, and there's a v final squared on the first one. And the second one looks exactly the same, except it's v initial squared. So that's just some little algebra manipulation there. So I'm getting that my net work is equal to this relationship, that's a pretty powerful statement, because now I'm saying that work was originally dependent on force and position, or change in position, displacement, right? Force and displacement, which is fine, and that's like the definition of work. But I can also say that my overall work is also, if I have final and initial velocity and mass, then I can find the overall work this way as well. And this is so important that we give these things names of kinetic energy. These terms are the kinetic energy of a mass. Anytime an object is moving, it has so-called kinetic energy. Kinetic just means like movement, sort of. So it's like movement energy. So we call this a kinetic energy term. And in fact, it's the final kinetic energy, because it's the kinetic energy due to a final velocity. And we call this term the initial kinetic energy, because it's the kinetic energy due to some initial velocity. So any object that is moving has energy, and has kinetic energy. And since work is a measure of how much energy is given to an object, then if I take the difference, overall the difference of the energy an object has from initial movement, initial speed rather, with the final energy, let me start over here. So if I take the difference of the final kinetic energy due to a final speed with the initial kinetic energy due to some initial speed, then overall that difference should give me the overall work. And that whole idea is can be summed up with this. I mean, it is just this, but if I use the delta notation, I can clean it up quite a bit and say that the net work is, or overall work, is equal to the delta KE, which just means the change in kinetic energy, which if I write it out more explicitly, this is exactly what it is. Okay. Let's see. Another way of saying this is that the overall work an object is experiencing is going to be due to how much speed it's losing or gaining. And I think the video, that initial video, does a better job of saying that, or they actually show examples, like with the skateboarder speeding up, he's given positive work, he's speeding up because his speed is increasing, and then later his speed is decreasing when he hits a wall. So he's that would be negative work. Okay, so I want to work a problem now dealing with this relationship. So what we're keeping in mind is that overall work is equal to delta KE, the change in kinetic energy. This is going to keep coming up. Overall work is equal to the change in kinetic energy. So let's say we have a 70 Newton force is applied horizontally to a 10 kilogram block at rest, which is at rest, for a displacement of 200 meters across a frictionless surface. How much work is done by the force? Call this part A. How much work is done by the force? Okay. Make sure that's going. Okay. So we have our force applied horizontally to a 10 kilogram block. So I have some force like this. I'll just say I'll say F sub A for like an applied force. I also have a gravitational force and a normal force, which in this case are equal, and I have no friction. So there's no friction force pointing to the left because it's a frictionless surface. Now, I'm asked how much work is done by the applied force. Right, so my normal force and gravitational force here are not playing a role. They're not playing a role. I could say something about them, right? In fact, they're going to be equal to each other in this case, but I don't really care about that. I'm asked about the work done by this force. Since the force is pushing the block and they're moving, the force is in the same direction as the displacement, I can just use that work is equal to F times delta X to get the overall work. Okay. I'm not introducing this idea yet. I'm going back to the definition of work. Okay, then that's going to give me 70 times 200. So I know that the force is applied in the same direction. The force is applied horizontally, so there's no cosine theta to worry about, no decomposition of vectors needed or anything like that. What am I getting here? 1400 joules. 1400 joules is the measurement for work. Now, I also know that this net work done by this force should be equal to the change in kinetic energy. So I know that 14,000 joules should be equal to the change in kinetic energy. Because this is the net work done by this force, right? Again, because these vertical forces are not playing a role here. delta KE now is delta KE is built from 1/2 mv final squared minus 1/2 mv initial squared. Hopefully we can set, usually one of these terms will go to 0 if we're lucky. Well, it depends on what the problem is asking, but let's see if one of them is 0. It says to a block at rest. So initially the block is at rest, meaning that our initial velocity is 0. So that means over here, I can say 14,000, I'll drop the unit for now since I'm doing math. I'll put the units back on at the end. 1/2 mv final squared, because the initial velocity is 0, so this term completely went away. And now I'm ready to go ahead and solve for, oh, wait a second, I already solved part A. I moved on to part B without even asking the question, sorry. Alright, part B is what is the final kinetic energy? Part B Well, I also answered part B. Part B is still, the answer is 14,000 joules, because why is that? Why is it exactly the same? Why is the final kinetic energy, which is just this one term, equal to 14,000 joules? Because the initial kinetic energy is 0. The initial kinetic energy is 0, so it's not contributing. Excuse me, it's not contributing. Now, here's the question I was moving on to. How fast is the block moving? How fast is the block moving? So let me pick that up. Got a little ahead of myself and just started solving immediately for the velocity. So let me pick up there. So we're starting here, 1/2 mv final squared. So I'm going to have v final just by doing some algebra, multiplying by 2 and then dividing by m. So 28,000 over m, which is 10, is equal to v final. Oh, I already said that. Goodness. All right. That's what I wanted. Square root. And I'm getting v final is equal to 53 meters per second. 52.9, what should I say? Yeah, 53 meters per second, that's good. How fast is the block moving? Okay. Okay, so part D now is, what is the acceleration of the block in the horizontal direction? Of course, in the vertical direction, there is no acceleration. Well, there's a couple different ways I could do this. I could say, by kinematics, I have, what do I have? I have delta x is 200 meters. I have v initial is 0. I have v final is 53 meters per second. And I have, well, that's let's see. Yeah, I don't have time, but I don't need time because I can use the equation I actually pointed out earlier, which is v final squared equals v initial squared plus 2a delta x. I could use that to solve for a. And I'll just say dot 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 because I think that you won't have any trouble plugging in and solving and getting 7 meters per second squared there. Also, I could, so as an alternative way of solving this, because now we've branched out of using, kinematics, we have other tools. We can also say, well, I know my force is equal to mass times acceleration, and I know my force is 70 newtons, and my mass is 10 kilograms times acceleration, and you see that much faster here that to get that A is equal to 7 meters per second squared. Both, I think, legitimate ways of solving this. Maybe this one is more efficient, but they're both legitimate ways to solve that acceleration problem. Okay. So we used. So the major point is that we were able to use this idea of work and energy being related with that relationship, where is it? Up here, that the net work is equal to the change in kinetic energy. Using that, we were able to find the overall speed. How fast is the block moving? We were able to find its speed. That's kind of the point of this problem. Alright, so now I want to talk about gravitational potential energy. So we have more than just kinetic energy. So overall, our overall work is equal to delta KE. We'll keep that in mind. But we also have potential energies. The first one we're going to talk about is called gravitational potential energy. Alright, so gravitational potential energy is just, it kind of describes what it is in its name. It's like energy that an object potentially has due to gravity. So if an object is on the floor, then it has no gravitational potential energy because there's no potential for it to like fall and gain energy. Whereas if an object is being held at some height, then there's potential energy. There's the potential for it to fall and gain energy as it's falling. So how can we measure this gravitational potential energy? Well, if I take an object that is at some height, how do I want to say, some initial y initial point, so y initial, and it's going to fall to y final. Let's look at the work done from here to here. Okay, so the work due to gravity, so I'll just for now just subscript that work due to gravity with a g, should be equal to the force due to gravity, so F sub g, times delta y. So I'm using delta y here instead of delta x, just because it's a vertical movement instead of horizontal. But it's still the same. It's still the same. Oops, that's my pencil notes. Where's my, it's still this idea that work is equal to force times displacement. And of course here in this case cosine theta is not mattering because gravity points down and this object is falling down, so they are in parallel to each other, so cosine theta is just 1 because theta is 0. The angle between the downward force and the direction of motion is 0 because they're in the same direction. Okay, so what is the force due to gravity though? If this is an object of mass m, same mass m, then the force due to gravity is mg, right? mg. We've drawn that a million times on our force diagrams, right? Force due to gravity is mg, and then I'm going to stack on delta y there. Delta y. Okay, I realized I left something out here, which is that delta y is actually being flipped around when we talk about this gravitational potential energy. What I mean by that is that I'm going to have, instead of y final minus y initial, I'm going to have y initial minus y final. So that kind of messes this up because of the delta y thing going, because delta y is understood to mean final minus initial, but I want it flipped because the object is falling and this is at, the ground where the position is 0. So I'm going to add a negative here and a negative here, and all that's going to do is say that when I expand this, instead of y final minus y initial, it's going to be y initial minus y final. mg y initial minus mg y final. And this is just because the object is falling down. And so the gravity and the displacement are going in the same direction. So this work should be positive, right? The work should be positive. But because of the way we define like downward as being negative, then that means, this y final is the ground. So this would be like 0. And this y initial could be like, I don't know, like 10 meters. So when I do this minus this, which is what delta y tells me to do, 0 minus 10, I end up with a negative. But that would mean that my work should end up being negative. But it shouldn't be because the force and the displacement are in the same direction. Work is only negative when the force is in the opposite direction to motion. So the way we account for that to make sure we're not breaking that rule for work is we say that the work due to gravity is equal to the difference in the two potential energies, but not final minus initial. It's initial minus final. Okay, we call these two terms. These are both gravitational potential energies. So the gravitational potential energy, as I said before, is determined by the height an object is held at. It's determined by its mass as well. So it's dependent on mass and height. And gravity, of course. We call this term, you might see U initial, U final. You also might see it written as UG initial for gravitational potential energy initial value and gravitational potential energy final value. Also, the most common one that I've seen is potential energy with a subscript Z for gravitational and then I for initial, potential energy gravitational, subscript F for final. One of the issues I see in the slides, in that slide presentation for this chapter, is that he uses all of them instead of just sticking to one. So let me say something about that. Typically, the capital U is used to denote potential energy, not specifically gravitational potential energy, but just potential energy in general. And there are other kinds. That's why I'm pointing this out. We're going to talk about another kind of potential energy with springs in this chapter. So typically U is used for just potential energies in general. So if you see a U involved, really it should be subscripted, or it should be obvious from context or something what kind of potential energy you're talking about. That's why you sometimes see people using the G to denote that this is gravitational potential energy. Also, just a different way of writing it is to use PE, which to me makes more sense for potential energy. PE G for gravitational potential energy, and obviously the I and F are meaning initial and final everywhere, but gravitational potential energy here too. This makes more sense. The U notation is coming from how this formula, I believe, if I'm remembering right, how it's derived in calculus. I think that's where the U is coming from. It's got its basis in some other formula in differential equations or something. I don't really remember, but this is the best to me because PE, potential energy, makes the most sense. Okay, so what can I say here? What kind of formulas am I pulling? Well, first of all, gravitational work due to gravity is going to be equal to negative delta PE. That's what I can say there. Because remember, PE delta PE should be final minus initial, but we're doing the opposite of that. That's why I introduced that negative, just to make sure that it's initial minus final. Okay. Also, just in general, potential energy is equal to mgy. So if I'm holding this pen or marker at which has mass, right, and gravity is constant at 1 meter, then it has some potential energy. If I hold it up at 2 meters, then I've doubled the potential energy. If I hold it up at 5 meters, then I've raised the potential energy by 5, etc. If it's on the ground and y is 0, then it has 0 potential energy. So potential energy is going to depend on where you've defined the ground to be. So often you'll see problems that say like it has potential energy blah 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 relative to the ground. You know, it'll say something or relative, it'll tell you what your surface level, your 0 point should be. So notice that potential energy is not, without the delta symbol, it doesn't have a delta y in there. It's just a position. Just a position. If you want a change in potential energy, then you're talking about a change in, you know, raising the height or lowering the height. So let's look at some problems with potential energy. Let's just start with a simpler one. How much potential energy does a 10 kilogram object if it is held at a height of 7 meters above the ground? So understood that the ground is 0 here. Well, this gives me everything I need to know. My potential energy. So this is not the delta PE. This is not asking for work. Work is not related here. There's no force either. It's just potential energy for an object. In fact, this object is just being held up. It's not moving, so there is no work being done. There is no force being done. The object is at a standstill, but it's at a standstill at a height, so it does have potential energy. It's going to have potential energy mgy, or mgh. You might see it written as h for height. I'm using y as in like a vertical, vertical y value. So I'm getting 10 kilograms times, of course, 9.8 times 7 there, just plugging everything in, and I'm getting a potential energy of 686 joules. So that's still measured in joules. Everything like work and energies they're all measured in joules here. Let's do another one. How about a monkey swings to a higher branch than the one it was sitting on. Then the one as it does the swing, the monkey's potential, the monkey's potential energy increases by 215 joules. If the monkey's mass is 6.5 kilograms, how much height did it gain? Okay, so we know that there is a change in potential energy here. So I know that the change in my potential energy is equal to 215 joules. And the change in potential energy, if I've written it this way, and do I need to worry about the negative here? Well, no, I don't think so, because that is only when we're dealing with work. And we could argue that work is involved here because the monkey's doing work by lifting itself to a higher branch, but I don't think we need to worry about that here. I think it's all gonna just the signs should fix themselves here for us. Let's see what happens. So we have delta PE, so that's the mgy final minus mgy initial should be equal to 215 joules. And what do we really want? We want change in height, or how much height did it gain, so we want delta y. We want delta y. So instead of writing it this way, probably better to compact it back into mg delta y, because we can't figure out like what height the monkey was at and what height it ended at, right? Not individually. We can't find y final and y initial individually. We can only just find out how much height the monkey gained. So we can say it gained, 5 meters or whatever it might be, but we can't say if it went from 0 to 5 or 5 to 10 or 10 to 15. We don't know that. We would have to be given a little bit more information, but we can at least find the change in height. So the way we're going to do that is with this formula, and we'll divide by mg on both sides. So dividing by mg, which we have the monkey's mass and we know gravity. So delta y should be 215 divided by, what was the monkey's mass? 6.5 times 9.8, which is going to be 3.38 meters. So that's delta y, and that's what we wanted. What if they said, what height did the monkey land at? Well, we would say, well, we don't know. We just know that it gained 3.38 meters. Okay. If we wanted to know exactly what height it landed at, they would have to tell us what height it started at. Like if they said the monkey started at a height of 10 meters, what height did it land at? Well, then we could say, okay, then it would be 13.38 meters is where it landed. So we started with a change in potential energy, and we were asked to find that change in vertical displacement, and that's what we did here. Okay. Oh, by the way, that last problem, I didn't bring up the change in kinetic energy, even though I could have. Where is it? Where did the monkey go? Oh. I could have brought up the change in kinetic energy, and we're going to find a way to relate potential and kinetic energy in a minute, but it's not really necessary to bring up here because all of this monkey's work is coming from his change in potential energy. So what I could argue is that his initial velocity is 0 because he's just sitting on a branch, and then he makes this huge jump up to another branch. So he's moving for a moment, and then he lands again, and his final velocity after he sits down again is 0 again. So this problem's not really about a change in speed. It's more just about that change in height. We could reframe the problem and say, how much speed does he need to cover this distance? I don't know. We could reframe it somehow to ask about kinetic energy, but in this case, it was not even necessary to bring in kinetic energy. Okay. So now let's go talk about connecting potential energy and kinetic energy together. So the first thing I have to say is that net force is equal to, right, delta KE, I already know that, but it's also equal to, hang on, what is it? I want to say this correctly. Work done by conservative forces plus work done by non-conservative forces. Conservative forces. We tend to write this as W sub C for work done by conservative forces plus W sub NC for non-conservative. So everything we've discussed so far are conservative forces because they do not depend on the path taken. They only depend on overall displacement. They don't depend on distance, they depend on displacement. So thinking about like an object being pushed horizontally from here to here, like that distance, that work done by this horizontal force to push the pen this far would be the same as the work done if I pushed it. So if I want to go from a distance from here to here, the work done to push it from here to here would be the same as the work done if I pushed it this way and then this way. Or if I took like some crazy route like this, but I still ended up back here. Or even if I went past it and then back. Because conservative forces don't care about distance covered, they care only about total displacement. So everything we've dealt with so far are conservative forces in conservative energies, like gravitational potential energy, dealing with that delta Y, that's a displacement, and the kinetic energy as well. Those energies are conserved. So examples of non-conservative forces, so things that do depend on distance traveled, would be like friction, what else? Air resistance, which really is friction. So friction's really like a great example of a force that's, a force that's non-conservative. Because why is it non-conservative? Well, because it depends on how much distance is covered. The friction gained by this pen moving from here to here is not the same as it moving from here back to here, right? It's gaining, like if I go all crazy like this and land it here, it's gaining more friction force, right? The more I move it. So friction is not a conservative force. Whereas gravity is a conservative force. Well, force due to gravity is a conservative force. Friction is not. So we have this relationship, and by the way, this is still equal to delta Ke, the kinetic energy there, kinetic energy. Okay. So in the case, I think I said kinetic energy is a conserved force earlier. I didn't mean that. It's the gravitational force is the conservative force. That's what I meant to say. Okay, so in the case where force due to gravity is the only conservative force involved, we will talk about another conservative force of potential spring energy. We'll talk about that too. But so in the case where force due to gravity is the only conservative force involved, and there are no non-conservative forces, we have this relationship. we have that, so gravity, force due to gravity is the only conservative force. This term is 0. We have that negative delta PEG for the gravitational potential energy. And remember, when we're talking about overall work here, we had to place that negative on it, is equal to delta KE. And that is going to be an extremely powerful relationship that you can take advantage of in all sorts of cases. But the point is, what's not involved here? There's no springs involved, which we'll look at in a minute, but there's no springs involved, and there's no friction involved. So what kind of problems can we solve with this relationship? And by the way, if I expand this out, what is this relationship? Well, it says that PEG initial minus PEG final. So remember, it's flipped around here. It's not final minus initial. That's why that minus sign is there. This is the necessary setup here when you're relating potential energies to kinetic energy and other energy in the system. You got to place a negative there. And this one is kinetic energy final minus kinetic energy initial. All right, so what if we have this setup, or this problem? A rock, a 3 kilogram rock is dropped from a height of 25 meters. Almost sounds like a kinematic equations problem. How fast does it strike the ground? Okay, so this rock is held at some height, so it has initial potential energy, gravitational potential energy. It has initial gravitational potential energy from that height that it's held at. PEGI, so gravitational potential energy initial, is going to be mgy, where, y initial, right? mgy initial in this case. So I'm getting that PEG initial is equal to the 3 times 9.8 times 25. Because my initial height is 25. My last height when it strikes the ground is going to be 0, right? What is this, by the way? 3 times 9.8 times 25. $735 joules. That seems wrong. Hang on. 9.8 times 3 times 25. No, yeah, okay, that's what I got. 735 joules. Now, my final potential gravitational potential energy is 0 because that final position is the ground. So I'm saying that this rock is falling 25 meters. Y final down here is 0, and Y initial up here is 25. What about kinetic energy? Well, my initial kinetic energy is 0 because it's held at rest and then it's dropped. My final kinetic energy is going to be 1/2 mv final squared. I'm looking for final velocity, but you can see now when I set up my equations here, these two terms go away. These two terms here go away, and I just basically set these two things equal to each other. I set PEGI equal to KEF. And let's see, can I just say V final will equal, not gonna, I think the algebra is not really gonna be an issue, so I'll say I'm setting that equal to this, so twice of that is 1470, and then divided by the mass of 3, so 1470 over 3 under a square root. Oh yeah, and we should say technically plus or minus. Technically plus or minus. hang on. Oh, dang. Right, so just introducing the plus or minus sign because of taking a square root on both sides, because the velocity was squared. And I'm getting that my velocity should be negative 22 meters per second. Negative 22. And why is it negative? Well, because it's falling down. It's falling down. I have to make the decision when I introduce that plus or minus which one to keep. And I know that I should keep the negative because the object is falling down. Okay, so you see how powerful this relationship at the top can be, because it allowed us to solve for the solve for the final velocity of this rock when all we had was its mass and its height. Nice. Okay. Now remember that this is the case when there is the only conservative force is the force due to gravity, and there are no non-conservative forces. That's why we were able to do this. So the more general relationship is that net work is equal to my conservative forces plus my non-conservative forces, which, by the way, overall should be equal to my change in velocity. So now if I look at the sled problem in the slides, this is the sled problem. I forget which number it is. I can't pull it up either. I'm afraid if I go try to pull it up, my camera will crash. It does that if I try to open too much, so I'm just going to call it the sled problem. It's probably problem 1 or 2. Okay. So we've got a sled. Oh, did I write down what I needed from it, though? Right. Okay, so we have a sled that was pushed. It's a 10 kilogram sled that was pushed with some force that gave an initial velocity of 2 meters per second, if I remember right. All right. And it's sliding on ice, and it's sliding to a stop. We know V final is 0 meters per second because it's sliding to a stop. We want to know delta x. We want to know, like, how long is it going to slide? Not how long, but how far, rather. How far it's going to slide. And we know that the coefficient of static friction on ice is 0.10. So friction is involved here. Friction is involved. What else can I say? Gravity is not really directly, gravity is involved because the normal force is involved anytime friction is involved, but the force that I'm really the forces that I'm worried about are that initial force and then the force of friction that's slowing down my my sled. So what I'm trying to say is that my work done by conservative forces is 0. That's what I'm trying to say. Because the only conservative force that could possibly be involved here is gravity. And while gravity is definitely involved anytime, you're talking about friction, gravity is pushing on the object, right? But the object is moving horizontally. Gravity's pushing down. Those are perpendicular, right? So hence the work done by gravity is 0 here. My work done, so that means my work done by non-conservative forces alone should be equal to delta Ke, the change in kinetic energy. This is like the exact opposite of the problem I just did, where it was the opposite case, right? It was just my conservative forces equal my potential energy equal to delta Ke. Now it's flipped. So we have to think about, what am I going to use? What is this work? What is this work? Well, it's due to friction. So this WNC is due to friction. It's a non-conservative force due to friction, but that's okay because we know about friction. I know that my friction force, F sub K, for my kinetic friction force, is equal to mu sub K times my normal force. But in this case, my normal force is just mg, right? Because I could set up the force diagram to show that, but we've seen that a few times, right? Where the if the thing is not accelerating in the vertical direction and it's laying on a level surface, then these two forces are equal to each other. Now, how do I get this to be a work instead of force? Well, I just multiply by the displacement. So my work due to friction, that non-conservative force, work due to friction, should be equal to that friction force times some displacement, delta x. So cleaning this up a bit, or rather plugging in what I know, I'm going to have mu sub k mg, that's my friction force, times delta x. Okay, moreover, I know that my my work done here by my non-conservative force, this thing should be equal to delta KE. So here is the big equation coming that's going to dictate this whole situation, which is that WNC is equal to delta KE. So I'm having that mu sub K mg delta x, that's the left-hand side, is equal to 1/2 mv final squared minus 1/2 mv initial squared. And now I'm ready to start plugging stuff in. Well, maybe first I should, what's the first step here when you're at this step? Do you plug stuff in or do you isolate the variable you want? I would say yes, the first step is that second thing I said, which is to first isolate the variable you want, but also look for things like things that zero out. So if my final velocity, right, from the top, my final velocity was 0. So this whole term goes to 0. Also, note that m is in all of these terms. Well, this one's gone, so this one doesn't matter anymore anyways, but m is in both of the leftover terms, so m just divides out. You'll see that happening a lot, like m doesn't matter nearly as much as you think it would. And in a lot of cases, you'll see that m just kind of divides right out. You don't have to notice that. It'll come out nicely if you do your math right, even if you do plug in m, but it's nice to notice up top because it cleans up your equations a little bit. So mu sub k g delta x, what do I have left? It's equal to negative v initial squared. Okay, so now I think I'm ready to go ahead and isolate delta x. I want to talk about that negative too. Why is that? Because you see that negative is going to be sticking around. I'm going to go ahead and just say what the solution is here, right? Assuming this is all fine. You know, v initial is 2, mu sub k is 0.1, g is 9.8, etc. So I'm getting 2 meters here. But, wait. I even said something about the negative and forgot to bring it up. Okay, all the way back here. So, yeah, what happened to the negative? Because delta x should be 2 meters. It's positive. So why is it positive? Where is the extra negative supposed to be? Because there should be an extra negative that is canceling out with the negative on the other side. What is happening is, where is my work due to friction? Here. My work due to friction, what's happening? Displacement, if the sled is being pushed to the right, displacement is to the right, but which direction is friction pushing? To the left. So that means that displacement is this way. Say it like this. Displacement is this way. Friction is this way. Then theta, what's the angle between them? 180 degrees. So really what I should have done all the way back here is go back to the very beginning definition of force, work, that talks about that cosine of theta, right? Cosine of theta. So cosine of 180 gives me -1. Essentially, all it means is that since my displacement is exactly opposite to my force, that I should have put a negative right here, a negative. and that means this negative would have been here, and then here, and here, and here, and that would have cleaned up my negative situation here, so that I end up with a positive solution. So that's something to keep in mind, that friction, you're going to be introducing a negative because friction is trying to oppose motion. So, and the motion being the displacement. So if friction is always opposing motion, then you should be introducing, when you write down your work due to friction, you should be introducing a negative sign there. I just forgot, I even pointed it out earlier in the problem, and I forgot to write it down. But sometimes that's how this goes. You get to like a certain point in the problem and you go, ugh, this doesn't make sense. I'm getting a negative, or getting like a negative under a square root, or I'm getting a negative displacement, which could be right if the object is falling. You just go back and think about the physical representation of what's happening, and once you think about it enough, you figure it out. Oh, also, the slides point out a fact about gravitational potential energy, that it can be negative if your y value is negative. Yeah, that's true. That would be a weird situation. This is not related to this problem. I just went back and looked at my notes and realized that they said something like that. And it just means that if you've defined the floor to be 0 and somehow your object falls below the floor, then technically it has negative gravitational potential energy, which would be a really weird situation anyways. But it's not impossible. It's not impossible. Now, let's look at another type of potential energy. Let's look at spring potential energy. Spring potential energy. Okay, so the force due to some spring depends on a couple things. It depends first on the size, and like size, when I say size, I mean like the thickness of the actual metal or whatever the material is. Depends on the size and material of the spring. Now we compact all of that information stuffed into a little coefficient called the spring constant, which we call lowercase k, the spring constant. It has units, by the way, newtons per meter. Force also depends on how far the spring is compressed or stretched. If you want to compress the spring more, it takes more force. If you want to stretch it more, it takes more force. The relationship is F equals negative K delta X. That K there is that spring constant. So that's traditionally given. It's like the coefficient of static friction kind of thing. Though I guess technically I shouldn't call it a coefficient because it does have units. The coefficients of friction don't have units, but K does have units, newtons per meter, which makes sense because if force is a newton, so if I'm saying K times delta X, then I better get rid of those meters units there, right? So, and this formula is just to be taken as, to derive it. This is a formula called Hooke's law. And to derive it, I think he derived it via like a bunch of experiments, and I don't know of another way to show that that is true. Intuitively, it makes sense, though, that the force to compress a spring would depend on how strong the spring is, like if it's steel versus plastic versus aluminum or whatever, how thick it is, right? Like the springs in a car, the shocks in a car, they're like super huge, so you could never, like a human could never like squish them because the material's so strong and large. And also, it makes sense that the force also depends on how much you're trying to squish or stretch the spring. So intuitively, this formula makes a lot of sense. As far as like really deriving it, I can't really do much other than just like point out that intuitively it makes sense. Let's talk about the sign though, because that's interesting. Why is the sign negative? Well, consider that I actually have a little spring here. Consider if I try to squish this spring, which I have to hold so it doesn't bounce away. If I try to squish it, and it bounced away. If I try to squish it to the left, like this, my finger is pushing to the left, then which direction, so my displacement is to the left. Which direction is the force pushing? It's pushing opposite, right? And if I stretch it, so now my displacement is to the right, which way is the force going to try and pull the spring? That way. Force, so this is called a restorative force because it always tries to restore back to equilibrium. If I compress it, it tries to stretch back to equilibrium. If I stretch it, it tries to compress back to equilibrium. Hence the minus sign. Hence the minus sign. Okay. I want to say that this is a conservative force. So remember earlier I made a big deal about saying that relationship we got for gravitational potential energy versus kinetic energy, that was only true if only gravity was involved. Where is it? And this is what I was getting at, because you can have, so this is what I said earlier, in the case where force due to gravity is the only conservative force, then we have this relationship. But there is another conservative force that possibly could be involved, and we'll look at like we'll expand this rule to include both of the conservative forces. So that's something we're going to do. But first I got to tell you about the energy due to a spring. Now the last two energies we were able to derive by looking at how work is done by a force like this. Right, so how can we derive the... Well, the naive thing to do, which honestly worked for the other two, is to say that work for this spring force, I guess just temporarily I'll say S, just for now for work due to springs, should be negative K delta X times another delta X, right? Another delta X, which gives me negative K delta X squared. And that's almost it, but really there's another term coming in, which if you've already looked ahead, you know there's supposed to be a 1/2 involved. So I don't know how to show that without calculus. In fact, I even looked it up on the internet to find like someone who derives it sort of algebraically or maybe intuitively or just with another method, and I didn't find any. So I guess that we're all just supposed to just take the formula without any kind of proof or anything. But here it is. The potential energy due to a spring is equal to 1/2 K delta X squared. Not delta X here, not delta, because this is just one potential, sorry. That's 1/2 KX squared, 1/2 KX squared, because it's just potential energy. It's not a difference of two spring potential energies, that will have a delta X in it, and we're about to look at that. But with just a single potential energy, it's just being held out at some X position, and it has potential energy. And then when I let it go, it moves to a different level of potential energy. So, let's see, what am I going to say now? Let's write down a very similar relationship to this, where I said in the case where force due to gravity is the only conservative force, blah, 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 blah. Let's write down a similar one here. In the case where gravity is not involved, and spring potential energy let me say spring force. Spring force is the only conservative force. And there are no non-conservative forces. Then we have this relationship. W net work equals conservative forces plus non-conservative forces should equal delta KE. My only conservative force is the my only conservative force is the spring force, so no gravity, and this term is 0, no non-conservative forces. I'm getting this relationship. Delta PES is equal to delta KE. Very, very similar to the gravity one. And yes, there's a negative there. Again, it's for a different reason. For the gravity, it was because an object is falling, and we're defining, there's a little weirdness there where we wanted to make sure our overall work was positive, even though that displacement was negative. So it's kind of a different thing going here, where it's more about the fact that our force starts off negative there because of that idea that the spring is always, it's kind of like friction, how it's always opposing motion, right? It tries to get back to equilibrium. So it's the same kind of relationship, and it's the same idea where you've got to introduce a minus sign just like gravity, but for a different reason. If I expand this out, I get this formula. It's exactly like the gravity formula. So this, on this side, I've got initial minus final, and on this side, I've got final minus initial. And also in the slides, he reorganizes this equation, puts all the initial stuff over here and all the final stuff over here. So if I really expanded this fully out, this would be 1/2 kx initial squared minus 1/2 kx final squared equals 1/2 mv final squared minus 1/2 mv initial squared. All right, let's do some problems with these springs. Let's do some problems with these springs. A force of 250 newtons is required to compress a horizontal spring 0.25 meters from equilibrium. So equilibrium is just where the spring is at rest. Equilibrium, not stretched or compressed. Find the spring constant. Well, we know that force is equal to negative kx, or delta x, in particular delta x there, displacement of the spring. That's the spring constant we're looking for. Okay. So the spring is like attached to a wall maybe, and we're compressing it like with some object, our hand or something, pushing it, compressing it 0.25 meters from, maybe this was the rest point. So this is at point 0, and we're compressing it that way. So since it's a compression, x final is, it's to the left, so we can say x final is negative 0.25 meters, and x initial at equilibrium is 0 meters. So that means that delta x is going to end up being negative, which is okay, because that's going to work out over here. Delta x, well, that's fine. So over here, I'm going to have that k is equal to negative f over delta x, just by solving this thing for k. K is going to be equal to negative 250. That's the force, right, required to compress this thing, 0.25 meters. And that's going to be 100 Newton meters. Oh, just kidding, it's miscounted my digits there. It's 1,000 Newton meters. No, 1,000 newtons per meter. 1,000 newtons per meter. So that's like a super strong spring, which makes sense because that force is pretty large, 250 newtons. 250 newtons there, and only to compress it, a quarter of a meter. So pretty strong spring. Okay. So that's just using that Hooke's law, F equals negative k delta x. Okay, let's see. How much energy is stored in a horizontal spring with spring constant, lost my place, 100 newtons per meter, 100 newtons per meter, stretched from 0.10 meters to 0.20 meters. Okay, so we're looking at energy here. If I write down my spring potential energy, I'm getting 1/2 kx squared. So I pulled this problem from somewhere online. I forget where I got it from, but I actually, now that I look at it, it really shouldn't. Potential energy is stored from holding something still out, like stretching this thing held at a certain point. So when it says from 0.10 to 0.20, that makes it sound like we're moving it, which is okay, but it kind of makes it sound like we're doing a different kind of problem. But really, all we need to note here is that the x that we're going to want to plug in is going to be, well, what is it going to be? Okay, I had to go back and look at it because I wanted to make sure. This is its rest length, which I didn't write down. From, I should say, its rest length. Its rest length of 0.10 meters to 0.20 meters. So that means that it was stretched to, how much was it stretched by? Well, 0.1 meters, 0.10 meters. And that's what's going to get plugged into our formula here. So we'll say 1/2 K, which is 100 times delta X, or just X here, the position. So is it delta X or X? Well, I guess you could argue that it's delta X, but it's really just how far it's stretched from equilibrium, like the position it's at relative to equilibrium. If equilibrium is not 0, then you do have to do a little bit of subtraction to find out how far it is from that equilibrium point. Okay, so here I'm getting 50 times 0.01, so I'll just calculate this as 50 times 0.5 joules. 0.5 joules. Okay, and by the way, spring potential energy, which is what this is always positive. Always positive. Because K will always be positive, and X, even if X is pushed into the negatives, it's getting squared, so X will not be contributing any negatives here either. So spring potential energy is always positive. The force, though, can be negative, right? The spring force, but the energy from the spring is positive here. Okay. So let's look at that problem. I think it's problem 2 in the text. I mean, in the slides, which is about a object being pushed down vertically onto compressing a spring and then launching the object. So that's the problem I'm looking at here. Actually, no, not yet. I don't want to involve gravity yet. I want to look at this problem. Let's say a spring. I want to do a horizontal compression first. A spring with spring constant 75 newtons per meter is compressed 0.375 meters by a mass of 1 kilogram. Find the speed of the mass, or find the speed of the object. I guess I should say the object. Find the speed of the object as it leaves the spring, once the spring is released. So let me draw a picture here. So I've got like some setup with a spring that's being compressed like by some plate or something, and we're about to launch this object. So it's compressed, it's got a spring constant of 75 newtons per meter. It's being compressed 0.375 meters by this mass, or we're compressing it, and this mass of 1 kilogram is here. We're going to let it go. We want to find the speed of that mass as it leaves the spring. So we can use conservation of energy here, of the conservation of mechanical energy, to say that, well, friction was not mentioned at all, and gravity is not involved here. So, or we're assuming gravity's not involved here. So we can say, well, I have this relationship. So I've got 1/2 kx initial squared minus 1/2 kx final squared, and on this side I have 1/2 mv final squared minus 1/2 mv initial squared. V initial, though, is 0. It's just sitting there. This term, let's see, X final is going to be 0 because that's where the spring hits equilibrium and it loses all potential energy, and the object is rocketed off of the spring. So I can say X final equals 0 because that is where the spring hits equilibrium. Equilibrium, and the object leaves the spring. So that's when the spring potential energy is turned into all the way. So the spring is compressed, all of the energy is spring potential energy. Then as it's launching, so in that like those milliseconds where it's launching, energy is transferring from spring to motion to kinetic energy, from spring energy to kinetic energy. And then right as it reaches that equilibrium point, the spring stops giving the object energy, and all of the energy is, for that instant, all of the energy is kinetic energy. And that magic moment happens at X final, that equilibrium point for the spring. Now, yes, in real life, the spring does go a little bit, it like bounces past equilibrium a bit, you know, which you can't even see with this because it goes so fast. But if I compress this and let it go, if I compress it and let it go, it bounces, it gets to equilibrium, probably stretches a bit past it, and then like bounces back and forth until it eventually reaches equilibrium. But we're kind of we're not worrying about that right now because those are small little movements anyways, and they would hardly contribute to any lost energy or anything like that. So what we end up having here is 1/2 kx initial squared equals 1/2 mv final squared. Now this is a problem where mass does matter. Mass does not divide out, right? If I solve for v final, I have a square root. Now the 1/2s go away, that's nice. So I have kx initial squared divided by mass under a square root, which is plus or minus. It'll be positive though, because the object is going. I didn't really specify which direction the object is going, so actually, if I really wanted to fuss about whether velocity should be positive or negative, I should have said back here that the object was launched to the right or to the left. I'll just assume it was, as I drew it, it's launched to the right. All right, and I'm getting v final is 10.3 meters per second. Oh, how did I get all that? Excuse me. X initial is 0.375. Actually, technically, since it's compressed to the left, X initial is negative 0.375, but it gets squared, so the negative doesn't play a role. K is 75 newtons per meter. Mass is just 1, and then square root. Let me double check that, because I wrote that down earlier. Let me calculate it now. 75 times 0.375 squared, and then, ooh, wait, now I'm getting a different answer. Yeah, I think I may have done something wrong earlier. Yep, I'm getting a different answer. 3.25. Say 3.3. 3.3 meters per second. All right, so now let's look at one where gravity finally is involved here. Let's put all this together. So if we do involve both gravity and spring potential energy, what we end up with is our overall relationship here is that the net work should be the sum of conservative work, or work due to conservative forces plus work due to non-conservative forces, which should altogether be delta KE. So if I assume a situation where, let's assume no friction, in other words, the work done by non-conservative forces is 0, but I will assume that there are springs and gravity involved, so maybe like a spring that's being compressed, a spring that's standing up. Where's my little spring? I think it bounced away. whatever, there it is. A spring pointing up being compressed, and also gravity being involved. What is that going to look like? We're going to have, whoops, not that. We're going to have negative delta E, PE for potential energy, gravitational, and also the spring energy also being negative, delta PE spring energy, so spring potential energy equal to delta KE. That's going to give us this big relationship that I'm going to just go ahead and write down, because we know that this would be PEG initial minus PEG final, and then minus, or actually the first term here would be PE spring initial, and then minus PE spring final equals KE initial minus, KE final minus KE initial, and then reorganizing it all. Basically, it comes down to this relationship, which is how the slides did it, which is stuffing all of the initial stuff on one side because they all have the same sign. It's just another way to write down this stuff, and then stuffing all of the final stuff on the other side. But you notice, like, it's kind of nice that when you do introduce gravity together with springs, the only way things get much more complicated is you just add in those two extra terms. Like, take these two gravity terms away, and that's what we were doing with the springs in that last problem. Take the two springs away, and that's like the problem with the rock, the 3 kilogram rock thrown off the cliff. So there it is. This is with no friction, no non-conservative forces giving any energy or losing any energy. All right, now I want to do problem 2. Because problem 2 from the slides deals with a vertical spring. So I'm assuming you can look at that as you're watching this, so I won't write down the entire problem. I will draw a picture though. So we have some spring launching an object. What I want to do is write down all 6 of these terms and see which ones are 0. See which ones are 0. Kinetic energy, initial. Well, initially it's just sitting at rest. The object is just sitting at rest, so kinetic energy is 0 for initially. What about kinetic energy final? Well, the question is asking how high does it, what height does it reach? But what happens at the maximum height? When you throw an object up, what velocity does it have at its maximum height? 0. So kinetic energy, while playing a role in this problem in between, because the object is launched, it's going fast, and then for a moment it stops as it reaches its maximum height. So it's got kinetic energy everywhere in between, but we're not interested in that. We're interested in this initial setup where everything's steady, and then at the end, when the object is steady again at its maximum height. So kinetic energies both are 0 here. What about gravitational energy initially? Well, that's 0 if we assume the ground, where the object is compressed to, best to assume that's the ground. Okay, so in other words, that's 0. Now the final gravitational, GF for gravitational final energy will not be 0. Right, this is going to be dependent on that height, which is exactly what we want. It's going to be dependent on that final y value, and that's what we're going to end up solving for in this problem. Now, what about the spring? I've got my PE potential energy, spring initial. Definitely got some initial spring energy, right? It's compacted. I'm going to just say 1/2 k y sub I squared. And notice I'm using y's instead of x's because it's vertical. Talking about vertical motion. And just like the last problem where the final spring energy was 0 when the object has left the spring, same setup here. So 4 of these are 0, and what do we end up with? We just end up setting these two things equal to each other. This is how these energy conservation problems go a lot of the time. You do a lot of setup trying to see how much stuff is going to 0, and then you end up with a lot of times just a really nice, clean equation that is pretty nice to solve here. Solving for y final, so without plugging anything in yet, I'm getting 1/2 k y initial squared all over mg. Notice m does not disappear here, because of course the mass matters. If it's a huge mass, it'll hardly go anywhere at all, whereas if it's a really light mass, it'll go really high. And I'm getting, just plugging this stuff in, oh, one second. Yeah, I want to say something here. This y initial is not the same as the y initial from the gravity. We should be careful of that. This is about how much the thing is compressed, the spring is compressed. This is about defining where the floor is for potential gravitational potential energy. So yeah, got to be careful there, because I said that this term is 0 because y initial is 0, which is true, but that's y initial for gravity, right? Over here, y final and y initial for the spring are different, right? They're different. The final value for the spring is, we've set to be 0 up at equilibrium somewhere. They're just different values, so just being careful there. Where does y initial come from? It's coming from however much it was compressed in the problem, like 0.1 meters or whatever it was. And K was given as like 5,000, I think. They gave it in scientific notation form. Yeah, 5 times 10 cubed, that's 5,000 newtons per meter. The mass is 0.25, and I calculated it earlier and I got 10.2 meters. I'm going to do it again and make sure I did that right. So I'm getting 500 times 0.1 times 0.1, and then divided by yep, okay, 10.2. All right. So that's everything for energies, I believe, and then the next thing to talk about is area under a work graph, like a graph that is measuring force over distance and how work is equal to the area under that, and also power, which is just a new definition, measured in a different unit and everything. So I'm going to record a different video for that if I have time this weekend, but I think this is enough definitely for a good start in chapter 5.